Okay, just going to go through the next PowerPoint here, which is on direct proportionality. Now, there's two key things you want to do inside this PowerPoint. We want to try and understand what direct proportionality means and look at the properties of a graph when two variables, say, demonstrate direct proportionality. Now, again, this is perhaps a term you've not really come across or heard of before, but certainly is a concept that you will have used probably every single day since you started using money. And a simple example of when you're in a shop purchasing something will demonstrate what direct proportionality means. You might just want to pause the screen and copy down these notes. So when you're purchasing something in a shop, the cost C is equal to the unit price P multiplied by the number of units N. And in symbol form, C is therefore equal to P multiplied by N. Now for an individual customer, and we're going to use this situation for our analysis now, the unit price P will be fixed as it's non-negotiable with the shop or the person who's working on behalf of the shop. Now this differs for large corporations which are able to benefit from economies of scale because of course they can maybe go about negotiating smaller unit prices when they buy items in bulk. So again, pause the screen and copy down these notes. So we can see there C is equal to P multiplied by N, where P again is a constant. Now if the price P is fixed, of course there's only two variables changing in this particular equation, those being the number of items you're purchasing and the overall cost C. Now I think common sense would indicate that if you increase the overall number of items you're purchasing, the overall cost will increase as well. And we say that the cost is directly proportional to the number of items. Now we can say that really in symbol form, that C is directly proportional to N. And this is the symbol we use here to represent direct proportionality. So again, you might just want to pause the screen and just copy down these respective notes. Now, we need to sort of understand in more detail, not just that whenever one thing increases, the other thing increases. We need to know exactly what happens. So I've got a really wee table here showcasing our independent variable N on the right-hand side. So IND represents the independent variable, and then cost is your dependent variable, DEP here. Now, let's say, for instance, we multiply the number of items you purchase by a factor of 2. So you now go up to the till, and instead of having one bottle of water, you've now got 2 bottles of water. Well, if you double the number of items you purchase, you will double the overall cost you have to pay for your purchase. If you were to multiply the number of items you purchase by a factor of 4, well, then the overall cost will also increase by a factor of 4. Similarly, if you were to multiply N by some strange number, let's say in this case 12.45, well, then the overall cost would also go up by a factor of 12.45 as well. Now, it does work in reverse. So if you now halve the number of items you're purchasing, of course, the overall cost will halve as well. And if we were to divide the number of items we are purchasing by 3.4, well, of course, the overall cost would also divide by 3.4. So if we just want to pause the screen and just copy down these respective notes, showcasing these specific examples that you do have to be aware of as well. Now, direct proportionality can be applied to a number of equations you'll encounter in your GCSE and your A-level studies, and a few select examples will illustrate this point. So if you just want to pause the screen, copy down these notes, and then we'll go through some of these worked examples. So worked example 1, just coming in really from Hooke's law, so F equals KE. Of course, the stiffness constant is a constant, it has that in its name, and therefore the stiffness constant K being a constant means that only really the force and the extension change, and therefore we can say that the force is directly proportional to the extension. Now, of course, if you're tuning in, you'll realize, of course, that applies up to and not beyond the limit of proportionality. That really means, of course, that whatever proportion f increases by, e must therefore increase by the same proportion. So if you multiply f by a factor of 100, e will multiply by a factor of 100 as well. Now, of course, the flip side of that is such that if you decrease f, well, whatever proportion f decreases by, then e must decrease by the exact same amount. So again, if you just want to pause the screen and copy down all these notes. In worked example 2, we're going to use a very straightforward equation. Speed is equal to distance divided by time. And if we rearrange that equation, distance is equal to speed multiplied by time. Now let's just say, for instance, that you're traveling down the road at a constant speed. Now, if the object is traveling at that constant speed, but really only the distance d and the time t will change. And because all other things are, constant, d is therefore directly proportional to t. And really the exact same as our previous example, whatever proportion t goes up by, d must go up in the same proportion. Whatever proportion t goes down by, d must go down by the exact same proportion as well. And again, pause the screen, just copy down these notes as well, please. Our final example here we can take in from P1, which is moments, and moment, of course, is equal to force times distance. Now let's make the assumption that the applied force in the system is constant, and therefore, of course, the only two variables changing are the moment, and of course, the perpendicular distance d. We can therefore say that the moment is directly proportional to d if the force is constant. Similar to our two previous examples, whatever proportion d goes up by, m must go up in the same proportion. Whatever proportion d goes down by, m must decrease by the same proportion as well. And again, just pause the screen and copy down these respective notes. That really ticks off the requirements of learning objective 1. Now, in the second learning objective, we need to look at graphs, and this is really important for GCSE, but also really stretching into your AS and A2 studies as well. Now, when two quantities are directly proportional to each other, and if they are then put onto the graph when drawn must be these following two things. It needs to be a straight line, and it needs to pass through the origin. Now, I can't stress how important these two criteria are for both your exams at GCSE, but also in the years ahead. Very, very common questions asked by SEA. So pause the screen and copy down all these notes, please. Now we're going to go into a bit more detail here as to why, why does it need to be a straight line passing through the origin? And hopefully the next couple of slides will illustrate that, just to give us a better understanding. So most students can maybe get those two criteria. Not that many can really explain the why. So let's say you've got some graph, you've got speed in the y-axis, t on the x-axis. If you go to some time t, you can then go up the graph, get to your line of best fit, come across horizontally, and read off the respective time t. You pause the screen, copy these notes down before we go on to the next slide. If we then decide to go till double that amount of time, so now going to 2t, so we've come across, let's say, 2 centimeters on your page. We now come across a further 2 centimeters to get to 2t. When you get to 2t, we can then take again a wee dashed line vertically up on your graph to your line of best fit, come across horizontally, and we can now mark in there what appears to be 2s. So it's 2 times the value of the previous s value. So again, pause the screen and you can just copy down these notes. Now, by having a straight line through the origin, and it's probably useful again to demonstrate this and draw this out, prove it, verify it to yourself. When we double the value of t along the x-axis, if you check carefully what you've done on your page, whatever number of centimeters you've come up vertically here to get to s, you should now be coming up double those number of centimeters to get to 2s. And that just verifies that whenever you double the value of t, you have in fact double the value of s in this graph as well, when it was a straight line passing through the origin. You might just want to pause the screen, add in those wee additional notes, and any supplementary data you feel might be useful to your graph as well. Now we're just going to try and demonstrate now what would happen if it was a straight line, but it's not passing through the origin anymore. In a similar sort of fashion, we could come across to some value t, the same as before. We can then rise up vertically until you get to your line of best fit, come across horizontally, and that's the respective speed at this time. Again, pause the screen, copy down these respective notes. If we follow out a similar process to before, we now come across to 2t, so it's twice the distance along the x-axis now. And if we now come up vertically, intersect the line of best fit, come across horizontally until we intersect the y-axis. Now you can see something doesn't quite appear to be right at the moment, but for now, can you just pause the screen, copy down these notes, and we'll explain really what's wrong on the next slide. Now you can see, of course, in this example, when it's a straight line that does not pass through the origin, we've doubled the value of t, but we have not doubled the value of s. So s, of course, goes from 0, 0 up to that particular speed, but you can see our new intercept value here. I've just labeled it some quantity x here, and you can see that is not twice as big as the original one. And so whenever you've got a straight line that does not pass through the origin, both quantities do not go up in the same proportion, and therefore the graph does not exhibit direct proportionality. And again, pause the screen and add in these additional notes to your slides or your booklet. And that ticks off really the requirements of learning objective 2, and that should hopefully be okay now in relation to direct proportionality.